This video covers section 19.7 to 19.10 in the Klein textbook. The first section that we'll discuss is the hydrolysis of acetals, amines, and enamines. Treatments of these functional groups with water results in hydrolysis in acidic conditions. So acetals reacting with water, this one forms acetone plus 2 molecules of methanol. Then with amines, this amine forms acetone again plus methylamine. And finally with enamines, here we form acetone plus dimethylamine. The mechanism is simply backwards for installing these groups in the first place. We start off with our acetal attacking the hydronium ion, and then we get to this cationic intermediate. We bring the lone pair down to form a carbonyl and eject methanol as a product. Then we attack the carbonyl with water, which forms this cationic intermediate, which we're going to deprotonate to make neutral. And in our next step, we're going to pick up a proton from hydronium again to form this cationic intermediate, and we can bring our lone pair down to form a carbonyl again, kicking out another molecule of methanol. And then we get to this protonated carbonyl, which we can simply deprotonate to get to acetone. And we're producing 2 molecules of methanol here. Let's take a moment to predict the product of the following reaction. Let's start just with the first one. So pause your browser. You have to notice where the carbonyl is going to be, and it's going to be at this blue carbon atom. So we're going to make acetone there, and then we need the remaining diol. So that's going to be this part of the molecule. Now pause your browser again and try to solve this second question. Again, we need to locate the carbonyl, which is going to be this carbon. So this is one of our products, and then the other product is methylamine. Sulfur nucleophiles behave just like oxygen. So in our first reaction, we have acetone reacting with this methyl compound, and we have an acid catalyst, and we need to remove water, and then we get the functional group of thioacetal. Similarly, we can form cyclic thioacetals using this dithiol. So here we're forming a ring where the 2 carbons in green are these 2 carbons. Rainy nickel is a reagent that we need to be aware of. This is also called spongy nickel, and it's a nickel aluminum alloy that contains mostly nickel. In this reaction, we have a thioacetal treated with Raney nickel, and that converts this whole group into an alkane. Next, we're going to move on to hydrogen nucleophiles. We're already aware of what these reagents are, so we first take lithium aluminum hydride followed by water, or we can use sodium borohydride with methanol to turn a carbonyl into an alcohol. Next, we're going to talk about 3 carbon nucleophiles. The first one is your Grignard reagent. When you treat a carbonyl with a Grignard reagent, you get an alcohol with your incoming Grignard nucleophile as the other position. Next, we'll move on to cyanohydrin formation. Here we're taking a carbonyl with potassium cyanide in hydrogen cyanide and making what's called a cyanohydrin. This reaction was originally done with hydrogen cyanide only, but it's better to have the potassium cyanide so that you have an abundance of nucleophiles present. The mechanism for this is pretty simple. We just attack the carbonyl and getting to this anionic intermediate, and then we protonate that anion with hydrogen cyanide to get the cyanohydrin. You might ask yourself, why not protonate the ketone first in this reaction? And the answer is that hydrogen cyanide is a weak base with pKa of -9. So in the equilibrium of the carbonyl with the protonated form, we greatly favor the left side of this equilibrium. Cyanohydrins are useful in future reactions. We can take a cyanohydrin with lithium aluminum hydride and convert this cyano group into an amine with acidic water and heat. We then transform the cyanohydride into a carboxylic acid. Our next topic of conversation is Wittig reagents, which are useful because we can install not only carbon atoms, but we can install pi bonds. And here we're using a Wittig reagent, which is a carbon nucleophile attached to triphenylphosphine. And whatever is attached to triphenylphosphine is going to be incorporated onto the carbonyl replacing the oxygen atom, and our oxygen atom is now part of triphenylphosphine oxide. This also works with R groups. So let's say we've got 2 methyl groups attached to the carbon, then we have 2 methyl groups in our product. How to make a Wittig reagent. Here we're taking an alkyl halide and we're treating it with triphenylphosphine, then followed by butyl lithium, and we get the reagent. And notice that this is in resonance with the form where there's no charges. So you'll either see this form or this form as your reagent. In our mechanism, triphenylphosphine attacks the carbon containing the leaving group, and the leaving group departs. Then we're left with this cationic intermediate. So we treat the compound then with butyl lithium, and we can write that simply as the butyl anion portion, and then we remove that proton and give the carbon an anionic charge, or -1 charge. Because this is an SN2 process, methyl halides and primary alkyl halides work the best. Secondary halides are slower, and tertiary alkyl halides cannot react at all. Let's do some practice. What Wittig reagent forms here? Pause your video and see if you can solve this problem. This is the Wittig reagent that forms. Let's look at the mechanism just to be clear on how this is made. We're taking our bromopropane and treating it with triphenylphosphine. There, we need our butyllithium, negative charge on carbon. This deprotonates one of our protons, giving you our final product. Wittig reagents can also contain when they contain alkyl groups, then we want to form the Z-alkene. Let's look at the mechanism for the Wittig reagent formation. We have our carbon nucleophile attacking the carbonyl, and our pi bond then attacks the triphenylphosphine phosphorus atom, and we form this intermediate that is got a neutral charge. Next we do another cyclic reaction, and then we form our product with triphenylphosphine oxide. When an electron withdrawing group or a phenyl group is attached, the E product forms. Look at these two examples below. In the first case, we've got an ester attached to the triphenylphosphine, and we get this E product where the ester is attached to the alkene. In the second example, we have the phenyl group as part of the alkene, and because we are in resonance, because we have resonance stabilization, then we also put our phenyl group at the Z position, at the E position. So the E product forms in these cases. Let's do some practice. Let's predict the product. Pause your browser and see if you can get this first one. Here we want to combine this carbon and this carbon, and then have the ethyl group hanging off. Now pause your browser and see if you can get to the second product. Here we're going through a two-step reaction where the product is an ether. Let's see how we do this. First, we're going to form our alkene product through the Wittig reaction. And I left off 2 carbons there, so make sure you add those 2 carbons. And then remember that when you treat an alkene with methanol in acidic conditions, we're going to form this intermediate, and then our alcohol attacks that, and we go through this this cation, oxygen cation, and we remove a proton and form our ether product. On our next slide, we want to identify the reagents for the following transformations. Let's pause your video and do the first one. This is going to require 3 steps. Here we're going to form our alkene, and then we're going to do an epoxidation, and then reaction with water in acidic conditions opens that ring, introducing a second oxygen atom. In the second sequence, we also have 3 steps. Pause your video and see if you can solve this. So in our first step, we need to install 3 carbon atoms because we have 3 here, and those are going to be these 3. And so we need to install an additional 3. So we've got 1, 2, 3 here for 1, 2, 3 there. That's going to give us this alkene intermediate, then treatment with elemental bromine gives us this intermediate. I'm drawing that without the isomers. And then in our final step, where we have 2 elimination reactions, then we form the alkyne. That's all for this video. I hope you found it helpful.